In this video, we're going to look at the other two shortcuts that we can use for counting problems, that is permutations and combinations. So for both permutations and combinations, we're going to develop and apply a formula we're going to use to certain problems. And we're going to determine the number of distinguishable permutations, something we're going to call the Mississippi problem. So first, let's talk about when we're going to be using this idea of permutations and combinations and when the fundamental principle of counting won't work. And this is the idea of replacement versus no replacement. So recall that what we talked about in the last video, the fundamental principle of counting allowed us to count the number of possible options when making a series of decisions. And we could represent those decisions as boxes and count the number of options in each box, and then we are done. So for instance, how many 4-digit PIN codes are possible if numbers can be repeated? What we can do, PIN code as single-digit numbers, we have 4 digits to look at. And we think about in each, how many options are there? Well, there are 10 single-digit numbers, 0 and then 1 through 9. And since they can be repeated, there are 10 options for each of these. And that means that total, we multiply all those together, we get 10 to the 4th options. Or we could just write that as a number. $10,000. Let's now look at the problem where we have 4-digit PIN codes, but for some reason the numbers cannot be repeated. So again, we still have our 4 boxes here, but now we think about how many options there are for each. Well, there are 10 options for the first number, but then once you choose that number, you can no longer use it. So there's only 9 options for the second, 8 for the third, and then 7 for the fourth. Each time you get rid of an option, so you're decreasing the number each time. We're just going to write this right now as 10 times 9 times 8 times 7. So this is the idea of repetition. Another way to think about that is replacement. So in the first, you think about you have these 10 numbers you can choose from. They're in a box and you're pulling them out. In the first problem, after you pull out a number, you put it back in, you shuffle them around, then you pick another number. In the second problem, you pick a number and then you leave it out of the box. You can no longer pick it. So this idea of repetition or replacement are kind of interchangeable in a lot of different contexts. So if replacement is allowed, we're going to use the fundamental principle of counting, and those are problems we've dealt with. If repetition is not allowed, we can still do some problems with the fundamental principle of counting, but now we have 2 new strategies we can use, permutations and combinations. So let's look at permutations first. We're going to use permutations when more than one item is selected without replacement. That's going to be a key thing here. And the order of selection is important. And note that the difference between permutations and combinations is going to be if order is important. If it is, we use permutations. If it's not, we're going to use combinations. So we talked about this example when we introduced counting. How many different podium finishes, that is first, second, and third, are possible in an 8-person 100-meter dash? So what we're kind of doing here is we are choosing 3 things. We're choosing a first place finisher, a second place finisher, and a third place finisher. And note that here, the order of selection is important. It is important that the first person is first, and second is second, third is third. If you change the order, it would be a different podium finish. So let's think about how many ways we could do this. Well, if you think about how many people could be the first place finisher, there are 8. since the first place finisher cannot also be the second place and the third place finisher, we take them out of consideration. And now we only have 7 people left that could be second, and then 6 people who could be third. And this is our answer, 8 times 7 times 6. At some point, we're going to stop writing down this kind of big number it's going to be for some of these problems. It's kind of more illuminating how it's sort of broken down. All right, so note that that's something that we could have done in the previous video, but let's talk about how this relates to something called the permutation formula. The number of permutations or arrangements of R items selected without replacement from a pool of N items. In this case, R has to be less than or equal to N. We denote that with this NPR notation. Sometimes you'll actually see this as PN, R, depending on kind of what source you're using. And the formula here is N factorial over N minus R factorial. So let's use this in the previous example and show how this works. So here in our first example, we had a permutation or arrangement of 3 items. We want to arrange the top 3 finishers, and the order is important. And there is a pool of 8 people that we are choosing from. 8 people total, and we're choosing 3, and the order is important there. And note that if we use the formula, here we have 8P3 is 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial. And this is something we did in the previous video as well. You can write this as 8 times 7 times 6 times 5 factorial. And we can cancel out the 5 factorials, and we're left with our answer of 8 times 7 times 6. So the total number of things we're choosing from is N. We only choose a subset of that, only a certain amount of them, R. That means R has to be less than N. And then we get our formula there. So let's see it in use a couple more times. Next example, 6 local bands have volunteered to perform at a benefit concert, but there is only enough time for 4 bands to play. There is also concern over the order in which the bands perform, for whatever reason you may want to imagine. How many different lineups of the bands are possible? So first, let's ask our 2 questions to kind of make sure we do have a permutation problem. Note here that we do not have replacement because a band cannot play in 2 spots. It's just going to be 1 spot for each band. So there's no replacements, and order is important. And that is going to tell us that we have a permutation problem. And why is order important is because they told us right there. So in this problem, we need to think about what is N and what is R. Well, there are 6 local bands total, and we are choosing only 4 of them to play. So our answer here should be 6P4, which is 6 factorial over 6 minus 4 factorial, 6 factorial over 2 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 6 times 5 times 4 times 3. which would turn out to be 360 different lineups. So note that we could have done this as well with our little box scheme. There are 4 bands to play. Our lineup is 4 bands. There are 6 options for the first, 5 for the second, 4 for the third, and 3 for the fourth. We multiply those together. The reason why we want the formula is we're able to take care of more complicated problems with that formula easily. And let's say that n was much larger than 6, then it wouldn't be really reasonable to do this box form either. All right, next example, a bowling league has 10 teams. How many different ways can the teams be ranked without ties in the standings at the end of the season? So note, again, there is no replacement. Why is there no replacement here? Because we have 10 different teams and they're all going to be ranked different. You can't have a team have the same rank twice. And here, order is important. Why? Because we are ranking them, and it's different if somebody has rank 1 versus rank 2 or something. If you're confused about when order would not be important, we'll see some examples of that in a little bit, and you can see the difference. But note, both of these just mean that we have a permutation problem. All right, so here there are 10 teams total to choose from. And a little bit weird here, we are going to rank all 10 of them. We're going to choose all 10 teams and look at all of them. Let's kind of see what this looks like with the formula first, and then we'll talk about it in some more detail. Here we're doing 10p10. That's 10 factorial over 10 minus 10 factorial. 10 factorial over 0 factorial. Remember in the last video we called 0 factorial is equal to 1 by definition. This is just going to be 10 factorial, different ways of doing that. We can do the box strategy here as well. But note that another way to think about factorials, n factorial we could say is the number of ways to arrange n objects. So if there are 10 teams, there are 10 factorial ways to rank those teams. The previous problem, we don't use just a factorial. I have to do a little formula here because we're not using all 6 bands. You're only using a subset of them. But if we use all of them, then we're just going to have this just this factorial. So I promised that I would talk about where 0 factorial comes from. Why is this 1? 0 factorial is 1. This is the number of ways to arrange 0 objects. And maybe it's getting a little bit philosophical, but there's not 0 ways to arrange 0 objects. There is one way, and that's to just not do it, just to not do anything. But that's a way of doing it. And again, the idea of the factorials, having 0 factorial equals 1, follows the pattern of factorials, allows us to do a lot of different things. There's a lot of reasons that all work together why 0 factorial equals 1. One of those is the number of ways to arrange 0 objects is 1 just by not doing it. Right? That's like there's one way to not do any chores, and that's to not do any chores, right? To decide to sit on the couch and not do anything. All right, so we have our permutations. If we use a subset of them, then we need the formula. If we're using all of them, it's just going to be just a factorial, but we can see that with the formula as well, thinking about the 0 factorial. Now let's jump to combinations. So again, we have without replacement, more than one item is selected. And the order of selection here is not important. So let's look at the example. 2 adults are needed to chaperone a daycare center's field trip. Abby, Ben, Christine, and David are 4 volunteers for chaperones. How many different groups of chaperones are possible? So here, a group of chaperones, it doesn't matter the order of that group. It doesn't matter if someone's the first or the second chaperone, it's just a group. So note here that order is not important. And we do not have replacement because you cannot have a 2-person group like Abby and Abby. 1 person cannot be 2 people in a group. So this tells us we're going to have a combination problem. We'll talk about combinations a little bit. Let's just reason this problem out real quick. Note that for some exercise here, I'm going to call Abby A, Ben B, Christine C, and David D. So let's think about all the different groups that we could have. Well, we could have Abby and Ben. We could have Abby and Christine. We could have Abby and David. Those are all the groups we could have with Abby. Now we could have Ben and Christine, Ben and David, and finally we could have Christine and David. And note that the order is not important. So this is the same thing as doing Ben, then Abby, and Christine, then Abby, and David and Abby. Ben and Christine is the same as Christine and Ben. Christine, David is the same as David, Christine. So here we have 6 different options. No, what we're actually doing here is we're finding sets of things, right? This is the set of Abby and Ben and the set of Abby and Christine, and the order of elements and sets is not important. All right, so now let's think about the formula we have for combinations. The number of distinct combinations of R items selected without replacement from a pool of N items. This is the exact same thing we said here, except we have without replacement as far as permutations goes. We have NCR. Note that sometimes this is actually read as N choose R, and sometimes this is actually written as this notation. It's like a fraction without the fraction bar in parentheses. And actually, I'm going to write that down because it's going to be one that actually pops up enough. N choose R is N factorial over N minus R factorial times R factorial. Let's see this formula in play on the previous example. So here we have NCR is N factorial over N minus R factorial R factorial. So in this problem, there are 4 volunteers total to choose from. That's our pool of volunteers to choose from. And we need to choose 2 of them. This is where the terminology choose comes from. We have 4 things and we need to choose 2. 4 choose 2. So using the formula, we have 4C2. Note this is the exact same thing as 4 choose 2 is 4 factorial over 4 minus 2 factorial 2 factorial, or 4 factorial over 2 factorial 2 factorial. This is 4 times 3 times 2 times 1, 2 times 1 times 2 times 1. Cancel out the 2 times 1, so we have a 4 and a 2, left with a 2 on top. Overall, we have a 6 total. So before we talk about stuff on the next page, let's actually think about this problem a little bit longer. What would be the case if order were important for some reason, right? That maybe there's a lead person in the group and then a secondary person in the group. If order were important, what would be the answer? Well, here I've kind of written them all down. We would have 12 different options. That is, we would have 4p2 is 4 factorial over 2 factorial, which is 12. All right, so just kind of with that in mind, now let's think about the next page. What is the relationship between combinations and permutations? There is clearly something very similar going on here, right? We have n choose r, we have npr is a very similar formula without the r factorial. And really what's going on is that we're really doing the same problem with one extra step in the combinations. So we can say that n factorial over n minus r factorial is the number of ways to arrange R objects from a pool of n objects. That's permutations. However, when we have those with combinations, the order is not important. So how do I get rid of the fact that order is important? Well, we are going to divide by all options that are the same to ignore the order. And there are r factorial options that are the same. Let's go back to our previous example real quick. We had 12 options total when order is important. But in this case, every 2 were the same. That was every 2 factorial were the same. So we take this 12 and we divide by that 2 factorial, then we get our 6 options total. In general, we're not going to divide by 2, we're going to divide by r factorial. Right, if we had 3 things, for instance, ABC, ACB, BAC, BCA, CAB, and CBA. These are all the options of 3 things arranged in order. That's 3 factorial. If order were not important, all of these are the same. And we could divide by that 6, by that 3 factorial, to get rid of the fact that those are all the same. The number of combinations, we could even say, is definitely less than the number of permutations. There's more options if order is important. All right, so what we just talked about for the last few minutes is really just to try to get a handle on where these formulas are coming from. They only differ by an r factorial in the denominator, and it's important to kind of understand where that comes from. So let's do some examples with combinations. As a member of a snack box subscription club, someone will receive 5 different boxes representing snacks from 11 different countries. Each box has its own country associated with it. How many different combinations of snack boxes are possible? So here, we're going to say that we have without replacement, as you're not going to get the same box twice. That would not be very nice. And here, order is not important because we just want to see how many different combinations. I don't really care when they come in, but I want to know what 5 countries am I going to receive in this. So here there are 11 different countries total to choose from, and we are going to choose 5 of them. So this is going to be 11 choose 5, which we're going to write as 11C5, which is 11 factorial over 11 minus, not 6, sorry, 11 minus 5 factorial times 5 factorial, which is 11 factorial over 6 factorial, 5 factorial. And let's just do some algebra with this real quick. This is 11 times 10 times 9 times 8 times 7 times 6 factorial, all over 6 factorial times 5 times 4 times 3 times 2 times 1. Our 6 factorials cancel out. That's nice. We could cancel out a 5 and a 2 and the 10. 5 times 2 is 10. What else can we do? We can cancel out a 3, and the 9 has a 3. We're left with a 3 there. We can cancel out a 4 from the 8, and we're left with a 2. And overall, this would be 11 times 3 times 2 times 7, which would give us 33, 66 times 7, 462. So note that we have calculators. We're able to kind of use calculators to do this, but this is how maybe you could do the calculation without a calculator. All right. If order were important there, mattered when you got each box, which one was the first one, which one was the second one, then there would be 11 factorial over 6 factorial total. All right, next example. A group consisting of 12 women and 9 men must select a 5-person committee. How many committees are possible if it must consist of the following: 3 women and 2 men? So this is a combination problem because if we have committees, it doesn't matter necessarily who's the first person selected or the second person selected. They're all just selected. They're all part of the committee. So here, order is not important, and we cannot replace because you can't have one person be 2 members of the committee. So here we have 12. So here, if we want to choose 3 women, there are 12 women total, and we need to choose 3 of them. Then we also need to choose 2 men, and there are 9 men total, and we need to choose 2 of them. And since we're making a series of decisions, we're going to take those 2 things and we're going to multiply them together. So first, let's take care of the 3 women. We can think about this as two decisions to make. We have our 3 women and then our 2 men. The 3 women are going to be 12 choose 3, and the 2 men are going to be 9 choose 2. And overall, this is going to give us 12 factorial over 12 minus 3 factorial 3 factorial times 9 factorial over 9 minus 2 factorial 2 factorial. That is 12 factorial over 9 factorial 3 factorial and 9 factorial over 7 factorial 2 factorial. Let's do these calculations out real quick. 12 times 11 times 10 times 9 factorial. 9 factorial times 3 factorial. 9 times 8 times 7 factorial over 7 factorial times 2 factorial. We can cancel out kind of the biggest factorial in the denominator. We're left with 3 times 2 is 6. Take that out of the 12. 2 times 1 is 2. Take that out of the 8. Overall, we could write this as 2 times 11 times 10 times 9 times 4 overall, which would give us a total of 7,920. So note that we couldn't really deal with that all in one big, calculation, just like one combination, because there's two different decisions we have to make, the women and the men separately. In part B, we don't have to divide up between men and women, so then total, we just have the 12 plus 9. We have 21 people total, and we are choosing 5 of them. So this is going to be 21, choose 5. 21 factorial over 21 minus 5 factorial times 5 factorial. 21 factorial over, not 6, sorry. 21 minus 5 is 16 factorial times 5 factorial. And I'll just leave that as is. We don't have to do that calculation over and over again. All right, combinations order is not important. Permutations order is important. So now let's kind of bring it all together. We have 3 different strategies we can use. The fundamental principle of counting, so we deal with any series of decisions, we can multiply them together. In fact, we used that in the previous page in part A here, because we had 2 decisions to make, and we just multiplied our 2 together. If we're selecting multiple things at a time and order is important, we use permutations. If not, then we use combinations. So here, let's do a problem where it's not clear just by what we're doing in the lecture if we have one or the other. We don't really know what strategy to use. Let's try to figure out which one it's going to be. So using a standard 52 card deck of playing cards, find the following. Note, if you are not familiar with playing cards, I urge you to just pause the video, look them up, and just kind of get a feel for the different kind of cards that there are. We'll talk about it briefly, but it's good to kind of know that as we're going to do a few examples with playing cards. So in these, we're going to have a problem that says how many different 5-card hands containing 4 kings are possible. So let's think about here that we have, first of all, we do not have replacement. Because you cannot have one card be 2 cards in your hand at the same time. You have to have 5 different cards. And also we have here that order is not important, as it doesn't matter the order of the cards in your hand. You can just shuffle them around and you still have the same hand. So this tells us that we are going to use combinations. All right, so now let's get into the problem. We know now we're going to do combinations. Let's talk about the answer. In a standard 52 card deck, there are 4 suits. We have our hearts, our diamonds, our spades, and our clubs. And then in each suit, you have 13 different cards. Ace through 10, Jack, Queen, King. 13 times 4 is 52. There's our 52 cards. So how many different 5-card hands containing 4 kings are possible? Note that there are 4 kings total in the deck. The king of hearts, the king of diamonds, the king of spades, and the king of clubs. So here we could think about maybe our boxes. Actually, I take that back. The boxes are not going to be very helpful here. Let's just think about we have 4 kings in the deck, and we want to have all 4 in our hand. That means our hand is going to include the kings of spades, clubs, diamonds, and hearts. And the 5th card that we have could be anything. All right, sometimes drawing pictures to sort of help illuminate what's going on is very useful. This is kind of like our box idea, but it's not exactly the same thing. So we have all 4 kings in the deck in our hand. That's like saying we have 4 things total, and we're choosing 4 of them. And 4 choose 4 is going to be just equal to 1. There's one way to choose 4 things out of a possible 4 things. But then our last card, which could be anything, there are 52 cards total, but we're not going to choose any of the kings. We're going to get rid of them. We have 48 cards left, and we're going to choose 1. And really, we actually don't even need combinations here. We can just say that there are 48 choices for there. You can think about this as combination. This is 48 choose 1 is just equal to 48. So there is our answer. There are 48 hands that contain 4 kings. The 4 kings are kind of already set in stone, and the last card could be anything, and there are 48 different choices. How many different 5-card hands containing 4 queens are possible? This is the same problem, because it didn't really make a difference whether I called them 4 kings or 4 queens or 4 jacks or 4 anything. We just said that, but that didn't really play any point in our mathematics. This is the same problem. There are 48 hands that contain 4 queens. All right, how many different 5-card hands containing 4 kings or 4 queens are possible? And here's an example where we're going to kind of go back to our set theory ideas in the previous video, or a couple of videos ago. This is looking at, let's call hands with 4 kings. Call this the set of hands of 4 kings. We'll call that K. And the set of hands with 4 queens we'll call Q. And here we're looking for the number of hands that have 4 kings or 4 queens, or being the union. And we know that this is going to be the number of K plus the size of Q minus the size of the intersection. So we just need to figure out what is the size of the intersection because we know that these are both 48. So this is saying how many different hands are there with 4 kings and 4 queens? Well, since we only have 5 cards in our hand, this would be equal to 0. This is saying that these two sets, their intersection is the empty set. So total, we have 96 hands that contain 4 kings or 4 queens. So now let's answer another question. How many 5-card hands containing 4 of a kind, that is 4 of any card, are possible? So let's think about this as we have a 4 of a kind here, and any other card. Well, the 4 of a kind, all we really need to choose is which card we have. We need to choose, are we doing a 4 of kings, a 4 of queens, a 4 of jacks, a 4 of fives? What are we doing? Right? And there are 13 choices here. There are n equals 13 cards, and we're choosing 1. Then, how many other cards do we have? As we've seen before, that's going to be 48. So total, there are 13 times 48 different 5-card hands with 4 of a kind, which is 624. All right, so this is kind of a hodgepodge of different ideas using kind of a different sort of things. And we'll do some more examples like this, especially in the worksheet, looking at some more complicated problems. All right, lastly, in this long video, we're going to talk about the Mississippi problem. Permutations with identical items, something we didn't look at before. So let's just start with this, with how many different ways can you arrange the letters of the word Ben? We can just do that. It is B-E-N, B-N-E, E-N, B, E-B-N, E-N, B-E, and N-E-B. There are 6 different ways to do that. You can think about this as order is important. N is equal to 3 different letters, and we are arranging all 3 of them. 3 with permutation 3 is going to be just equal to 3 factorial, which is 6. That's not what we've done before. We're just thinking about a permutation here. Now let's think about the letters of the word B. Well, similarly, we have B, E, E. Let's call this E1 and E2 to kind of differentiate between them. B, E2, E1, that's kind of something different. How about we start with E1? And we'll start with E2. So that would be what is the case if the E's were differentiated from each other, but they're not. These two are the same. They're both just B. these two are the same, EBE, and those two are the same, EEB. In this case, there are only 3 options. Because we have the identical letters there, not every different arrangement is going to give us a different word. What we're really doing here is we're taking the total amount of options, 3 factorial, and we are dividing by 2 factorial. And the 2 factorial here is the number of ways to arrange the 2 E's. Right? Do we go E1, E2, or E2, E1? We're just going to divide by that similarity. In general, we can do that, the number of distinguishable permutations or arrangements of n items in which x items are identical, y items are identical, z items are identical, and so on, is n factorial over the x factorial, y factorial, z factorial, and then more if we have them. And this is where we get to calling this the Mississippi problem, because Mississippi is a word with a bunch of identical letters. So how many different ways can you arrange the letters of the word Mississippi? Note that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters total. But we have 4 S's. We have 4 I's. We have 2 P's. And we have 1 M. So rearranging letters in the word Mississippi, just like that, has a bunch of different options that are all the same. Right? You could rearrange all the S's in any order, and you get the same. You could rearrange the I's or the P's, you get the same. And there are 4 factorial, 2 factorial ways to rearrange them. So total, we're going to have 11 factorial ways to rearrange the letters. But if we rearrange the S's in any way, then we're going to get the same answer. So we can divide by all of those similar options, which there are 4 factorial. We could also rearrange all of the I's in any way. We could also rearrange the P's in any way. And even though we didn't write it down, we could actually rearrange the 1 M in any way. And there's that 1 as well. And this is our answer. 11 factorial over 4 factorial, 4 factorial, 2 factorial, and an optional 1 factorial. We're going to use this kind of counting periodically when we have identical things. It allows us to do a lot more ideas. And this was just a brief introduction to the world of counting. Counting problems can get very complicated very quickly. These are kind of the basic tools to be able to tackle all different kinds of different counting problems.